So for this video, we're going to review some concepts covered in General Chemistry 1 and General Chemistry 2, and then we will build upon these concepts in later videos. So the first thing I want to talk about is what's called an Arrhenius acid. So Arrhenius acids, what they do is they form H+ ions in solution, so they form hydrogen ions in solution. We can also think about Arrhenius acids as forming H3O+ or hydronium ions in solution. So for instance, if we take HCl and we put that in water, what's going to happen is we're going to form H+ aqueous ions and Cl- aqueous ions. So that's one way to think about the dissociation of a strong acid like HCl. So in the case of HCl, we indicate full dissociation with a single arrow. We can also draw out this reaction as such. We can say, okay, imagine we have HCl in solution and we add water. One way we can denote the Arrhenius acidity of HCl is to show that in solution, HCl forms H3O+ aqueous and Cl- aqueous. So by definition, HCl is what's called an Arrhenius acid because it generates H+ aqueous cations or hydronium ions in solution. So that's an example of an Arrhenius acid. Now, what an Arrhenius base is as follows. So, if I can get this to work. An Arrhenius base that forms hydroxide or OH- ions in solution. So one simple example is if you have, for instance, sodium hydroxide and you put that in water, what you're going to generate is you're going to generate sodium cations and we're going to generate aqueous hydroxide anions. I've seen it different ways, but I always like to put the negative charge by the oxygen because that reminds me that the oxygen is what has the negative formal charge in this acid-base reaction. Another example of an Arrhenius base is something like ammonia. So NH3 plus H2O. What happens here is that in solution, the ammonia will actually pick up a proton from the water, so it generates NH4 plus aqueous plus OH- aqueous. So here we can define NH3 as an Arrhenius base because it forms hydroxide ions in solution. Notice for this expression I use the double arrows. This means that there's only sort of partial dissociation, or this is only happening some of the times, as opposed to a single arrow, for instance, with sodium hydroxide, which shows that sodium hydroxide is fully dissociating. So that's the Arrhenius acid concept. The next concept I would like to cover is the Bronsted-Lowry concept of acid basicity. So Bronsted-Lowry concept. Okay. So here, what an acid is defined as a proton donor, and a base is defined as a proton acceptor. So imagine in solution we have the hydronium ion, and we have the nitrite anion. And in solution, what can happen is the anion can accept a proton from H3O+, and what that'll generate is H2O, and it'll generate HNO2. So according to this concept, the Bronsted-Lowry concept, the acid is the proton donor, the base is the proton acceptor. So notice in the reactants part of the reaction, we only really have one thing that can donate protons, right? Because the NO2 minus does not have any protons. So H3O plus in this example is the acid, NO2 minus is the base, and they react to form H2O and HNO2. The Bronsted-Lowry concept introduces the term conjugate acid and conjugate bases. So when you think about this reaction, we have our acid reacting with our base. What this is going to form is this is actually going to form a conjugate acid and a conjugate base. So what the conjugate base and conjugate acid are, if you think about going backwards in this reaction to get to our original reactants, the conjugate acid would need to give a proton to the conjugate base, and the conjugate base would need to accept a proton from the conjugate acid. So that's the Bronsted-Lowry concept. The last concept that we'll go over that's super important for inorganic chemistry is the Lewis acid definition of what an acid is. So we can talk about acidity in terms of Lewis acids / bases. So I always remember a Lewis acid accepts electrons. So imagine we have the example of we have BF3, and that is going to interact with something like NH3, so the way this reaction works, where BF3 reacts with NH3, is that boron can actually accept additional electrons, because note it only has 6 electrons, so the boron can get this lone pair from the nitrogen, and it can form a complex that looks like this. So we could actually talk about this in terms of acid base chemistry. So here BF3 is acting as the Lewis acid because the Lewis acid is accepting electrons, and NH3 is acting as a Lewis base because it is donating electrons. So this comes into play a lot, Lewis acids, Lewis bases, when we're talking about coordination chemistry. And we'll continue to talk about this later today.